Okay. Good evening, class. So today we will be discussing our last part of the electrostatic chapter. Uh, we will also cover the some applications related to the electrostatic sensors. Uh, and if we find some enough time at the end, then we will discuss the midterm. So I have marked the midterm test, so I'll give you. Okay. So first, let's put some time to discuss the lecture, and then we will come to the midterm discussion. Okay. So I give you a quick recap about our previous discussions. We discussed about the charge distribution. We discussed about the Gauss's law, Maxwell equation. So how the charge can produce electric field, right? And how the divergence of the field displacement D can give us the charge distribution. We also looked at the theorem. So how to move from the volume integration to surface integration, okay, divergence theorem. Uh, Later on, we developed some relationship between the electric field and voltage. So if you are given voltage, how to find out electric field, and if you're given electric field, how to find a voltage. Today we will discuss these things and try to converge the discussion. Okay. Of course, electrostatistics is a very wide field. Okay, so we cannot complete all the concepts, right? So, but we will try to put some light on important concepts as well that are remaining. So far, we have learned that the voltage difference or potential difference is the line integral of the electric field along the path, right? So the negative sign shows the polarity. So similarly, we can find out the voltage if we are given charge density. Now, these relations are very helpful in understanding the voltages across any electrostatic system. It can be applied to the capacitor plates as well, right? We also looked at the differential way of looking at the voltage is to first apply the negative of a gradient on a voltage, and then you can get a function of electric field that is actually generating those voltages. Okay, so these are the two important relationships. Uh, Today we will just go through one of the small topic, which is the dipole. Dipole occurs in the electrostatic field quite often. So it is a result of an external applied electric field to a material where the two charges that are being pulled together at some distance d, right? So that actually means that there's a dipole. So there are two oppositely charged charges that are displayed at a distance d. Now this happens at a molecular level. Okay, so that happens at a very, very small level inside the material. Okay, so if you are providing an electric field to a certain material, so the molecules inside we will discuss this later, but that can also happen across some electronic devices, right? Such as if you have a two plates or two conducting polarities of two terminals that are separated by some the dielectric material, right? So it's a general phenomena. So the device that we use for this concept is capacitor, but that can applicable to any other electronic or electric models or systems that actually exhibit the same property, right? So if you have one charge at one plate or another charge at negative, and then there's some distance between them. So I'm not going into more detail, but we can still derive the voltage between these 2 points, or the if you have two charges displaced at distance d, we can again use the same formula, 1 over 4 pi epsilon naught q over r1. So the voltage is v1 minus v2, right? So because the other charge is negative, so you use minus q over r2. Now, because these two are separated by a small distance, right? So these these charges, they can be sensed at any point P, right? So r theta phi. Now this is like a spherical system, okay? So we can have r1, r and r2 distance, which are almost approximately at the same distance because the lengths can be treated approximately same. Attention, please. Please look carefully. Uh, we can again do some approximations. For example, r2 minus r1 is almost equal to, let's say, d cos theta, this difference. And these two are, let's say, similar, then we can replace with r square. So we can come up with this formula qd cos theta or 4 pi epsilon r square. Remember, when we energize or we apply the electric field to certain electrostatic charges, we are often interested. Please listen carefully. We are sometimes interested in the electrostatic force, right? That the force that the charges they feel when they are under the electric field. So this formula is very useful when we are trying to find out the dipole forces or the torque created by the electric forces. Now, in this formula, we can use qd cos theta into qdr, just a dot product, and then modify the formula here. In this case, the distance d and the charge q, they can be treated as a dipole moment, right? And then we can use this formula. So later on, we can apply this to our the spherical system gradients to find out the electric field caused by these, the dipoles. This is also helpful in analyzing the certain chemical bonds behaviors as well, right? So if you have some materials that have some bonds that they have the dipoles across their terminals, so we can easily find out the voltages and electric field. Now, this can be different in different scenarios. For example, if you have a positive and negative charge, right, and applying some external force, if they are separated enough. Remember, positive and negative actually attract each other, right? So if there's no electric field, of course, all the positive and negative charge will align each other in such a way that they will cancel the effect, right? Because they have to be in an equilibrium position, equilibrium state, right? So you would see that they are separated. That means that there is some external force that is causing them to separate, okay? In that case, you would see that the electric field would follow the same pattern. In the later part, we will discuss more about these patterns, but I can show you uh, some patterns. So let's see the pictures. So you can see a simple charge. Right? It's a dipole due to a single charge, and then there are more charges. If there's a disk here, right? So this, you see that the red corresponds to the positive, and the blue corresponds to the negative. If two charges are separated enough, then it should be like this. If we have a disk, then you see that these field line will follow this. If you have a capacitor, you would see it would follow like this. Uh, Here, I would ask you to think about one more thing, that you would see that in all those cases, the electric field always try to keep itself perpendicular to the surface. Right? This is very important. We have been discussing this for a very long time. Right? So you would see that the electric field pattern at every single point on the surface is perpendicular. And as it goes to the edges, again, it will try to tilt up in such a position that it's always perpendicular. Okay. Now you see this one, right? So they are always perpendicular. You see, this one is perpendicular, this one is perpendicular. Okay. Okay. Now, if you move to the other slides, we have some videos here, but I'll show them later on. We have this simulation for you to try. And here are a few tutorial questions that actually belongs to the previous topic. Okay. But we can also try them later on. This is the same question we discussed in the midterm, that if you have 4 different charges, then you can find out the position vectors first, right? And then you can find out the forces, right? So Q, Q1, Q, Q2, right? And then R minus R1, R minus R2, R minus R3, right? So we have done it before. This is another tutorial problem uh, that asks you to find out the E, or the electric field, due to the infinite line of charges. Now, you should know that the E for infinite line of charge is equal to rho L divided by 2 epsilon naught R here, right? Along with R unit vector. So if you're wondering where we have got this formula, so we need to go and see the application of Gauss's law, right? So if you see here, right? So we use this along the application. If we apply the Gauss's law, okay, so we get the line charged electric field, rho L over 2 pi epsilon naught R. Okay, so we can use this formula here. Okay, uh, because there are two line. Attention, please. Please attention. So actually, we are asked to solve this, that there are two lines here, right? And they are actually 2 centimeter apart at +1 and -1 if the axes are in centimeter. So now the question is that there is some y-axis. So you find electric field anywhere along the y-axis, anywhere. So let's say if I'm interested to find here, then this one is my y-axis. Okay. So I'm trying to find out the electric field at this point. Okay. So again, the formula is very simple. So I try to use the electric field on both lines and just add them together. So in fact, this question is trying to use the power of the the vector algebra. First, how to find out the unit vector. So R1 is equal to vector R1 over the R, the amplitude. Okay, this one is magnitude. So the magnitude vector is the vector itself is minus x plus y. So y, it's because this value is 1, right? And this value is y, okay? And this value is minus x times 1, and this value is y times y, okay? So we add them together because x magnitude is 1 and y magnitude is simply y. So 1 plus y, okay? That's why we have this vector. Similarly, R2 is equal to x because the value of x is 1 here, and value of y is y, and the direction is y. Okay, so this will give us the magnitude of R1 equals to 1 square plus y square under root, and this one will also give 1 square plus y square under root. Okay, so these are the two magnitude. That's why you would see that the R unit vector and R2 unit vector. Like, yes, yes. Okay. So let's continue, and I will upload soon. Okay. So we have now R1 and R2 vectors, and now we plug in with this main formula here, right? So these are just the tutorial problem from the previous topic. So E1 plus E2. So E1 is row L1, which is actually both have the same row L. So this one is row L line and row L line. So it should be like this. Okay. And 2 pi epsilon naught r. So r is given 1 plus y square under root. When you plug the unit vector, 1 under root times another root times become power 1. Okay. Right. So this becomes power 1. Okay. Because there are two under roots. Thank you. So, and then you can simplify them. X and X will cancel out, and Y can add up. Now, this shows that at this position, right? So one vector has X like here, another has X here. So they can cancel each other. And Y can add up, and the main field is along Y direction. Okay. So this is the application of the electric field of due to two line charges. Okay. And then we have another application. We have a spherical shell of radius A. You see, it has a radius A. This is the shell. This black is the shell. Now we have two regions, one and two. One is inside and one is outside. The charge density is rho s. We are asked to find out the electric field by using the formula of electric field and find out the the Gauss's law, apply the Gauss's law and find out the electric field. So we know that d dot ds is q. Remember, this is a like a generic questions. There are no proper values, right? But you just use the the symbols as a value to solve it. Now, if there are generic questions, if there are no perfect values, then we can say that the d vector is equal to the d magnitude and the d direction, right? So d direction is usually r. Therefore, we use this one. Okay. So that's magnitude, and that's the r unit vector or the direction. Okay. Now, d can be written like this, and area is along this. So for the sphere, remember, ds, you can directly use 4 pi r square. Then you no need to solve for it because it's already known. It's a sphere. Now we can quickly simplify the question. D dot ds is equal to dr is the magnitude, ds is 4 pi r square, and which is also equal to q, right? So q comes directly from here. Okay. Now the d is equal to q or 4 pi r square. Because we are asked to find out the electric field everywhere, now we have two choices. First, we go inside, and then another, we go outside. Inside, there's no charge, right? Because the charge is always spread on the surface. And the inside, there's no charge. Therefore, the electric field is zero. Okay. This is an important point. I will discuss again later with some videos so you can understand. So the electric field inside is always zero. For a Gaussian surface of radius r2 is greater than a, that means that's above the surface, right? Above the surface is q is equal to rho s over 4 pi a square, because this is the formula of a charge. Remember, charge density equals to charge per unit area, right? Right. So we can directly sometimes write q is equal to rho s times 4 pi a square, not r square, because a here is the radius. Okay. So do not confuse. Now, charge is known, and electric field is equal to the field displacement divided by the epsilon. So we know the direction r, the amplitude is d, d is known here. So equation number 1 here, equation number 2 here. So plug all the values here, and then at the end you will get the electric field. So this is electric field of a charge density at the surface of the sphere. You remember, rho s a square over r2 square, right? So r2 is this one. So as you move away from this A square, right? A increases, 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 then these two become same, and then they can be cancelled out. Okay, that's the electric field due to the sphere. Now, here is the demonstration. Remember, we always discuss that the electric field is perpendicular to the surface. Whenever there is a charge accumulated at a certain surface, right? So the charges, uh, uh, they experience certain force, right? So what type of force? Let's say there's a attraction between plus and negative, and there's a repulsion between plus and plus. So the charges have a choice, so they can move without any external field. They can move by themselves, just like similar to when you pour the water inside any glass. So it takes the shape of any container when you place it, right? So similarly, the charges, when they have some charges on the surface, they need to adjust themselves in such a way that the net electric field is zero, right? Therefore all the charges, they move up to the surface, and then they align themselves into such a position that they are always perpendicular. Now, I I remind you to to recall the video of the. Remember, we look at some video of a pot when we charge it, right? So we saw that the charges at the greater surface are, the density is small, whereas on the edges the density is more high, right? We measured it using the experiment. So there's a reason. You see, if you have some surface like this, right? If you have some surface like this, right? Now you see, uh, here the charges need to be very, very far so they can make themselves perpendicular. Okay, but at this position they need to be very, very close so they can remain perpendicular. Understand? Did you understand? So that's the concept. The charges, when they are placed on a surface, they try to keep themselves in such a position that the electric field vector is always perpendicular, right? If the electric field vector goes like here, then there's another force, so the charge readjusts itself, right? So later on we will see that. That's the reason you would see that most of the lightning attractors at the top building, they have a needle like structure. Have you seen the lightning arresters? Anyone? Does anyone knows the lightning arresters? These are the topics that we are going to discuss today. See like this? You see like this? So they actually capture the high charge accumulation at the surface of the earth, right? So when there's a rainy season, right? So the charge accumulation, they get closer and they build up a high charge. That means high and strong electric field, right? So what is the purpose of making a needle, right? So there's a huge charge accumulation at the center top, and then it can easily find out the way to discharge itself through the air. Now later on we will discuss that that air is actually the epsilon that we are more interested in, right? So let's move back to our original discussion here, right? So still the charges, they will always adjust themselves in terms of the distribution, the density, such that they always align themselves to make them perpendicular to. So all these demonstrations will teach you the orientation vectors. Okay, uh, now let's look at some of the properties that we have already discussed, but let's look them again. That uh, in order to understand the characteristics in electromagnetism, we need to look at the materials and how they behave, right? For example, if you are interested in understanding the electrostatic characteristics, right, definitely you are looking for conductivity, right? Remember, resistance is not a standard parameter, right? It's not a characteristic parameter for finding the flow of electron, right? Resistance is just a ohmic value, right? However, 1 over resistance is the conductance, right? What we call the Siemens, right? Conductance. And for a standard uh, consideration, we need a unit of length, what we call the conductivity, Siemens per meter. Now you can compare, you can put them into a generalized form, so you can standardize the values, and then based on this value, you can rank the different materials into a certain value of conductivity. Now, we can have a band of values, or you can put them into 3 different categories. You can call them conductors, you can call them non-conductors or insulators, right? And then you can have a semiconductors. Uh, for insulators, because insulators, we call it the bad conductors, right? Now, the bad itself again defines how bad. So how much current they still allow, right? That depends upon the application as well and the rated values of the voltage we will discuss now. So insulators or dielectrics that actually do not provide any free electrons, or that do not provide any mobility of electrons when an external electric field is applied, right? So on the top, we would have a silver, right? So the conductivity is very high, right? So when you apply the electric field, so it will easily apply the electron mobility, right? Therefore, you will see there's a conduction current. Now, uh, we can see the conduction current. I'm saying conduction current. It's not uh, the the other currents, right? That are due to the physical motion of the conductor. So not the convection, just the conduction current density is equal to conductivity times electric field. Remember, this is something analogous to the Ohm's law, that V is equal to IR, right? So V is now the analogous term of E, R is analogous term of sigma, that is conductivity, and the I is from the J. That is a special case of Ohm's law, right? So that's the basic Ohm's law. That's the derived Ohm law. So for a perfect dielectric, uh, sigma is 0, right? In contrast, a perfect conductor is a material with sigma is infinite. So perfect actually means the ideal, right? So you would see that the conductivity is almost infinite, right? That means very, very high for a perfect conductor. That means there is no opposition to the current, right? And whenever you apply the electric field, it can produce the high the transition or the motion of electron. But there are certain categories within the conductor. So you have superconductors. Of course, there's no infinite sort of thing. For the dielectric, we know the sigma is 0. Now, because because when in the dielectric, when you apply electric field, please listen carefully. For a dielectric, let's say glass or mica, when you apply electric field, right, there's no current, correct? Let's say the insulators that we use in the power transmission lines, okay? So still we have a high electric field, but there's no current density. There's no current flowing because the sigma here is actually 0. That's due to the 0. Even though there's a E, but this 0 makes it 0, okay? Now, look at something more interesting. Uh, the conductivity actually comes with more other parameters. For example, you can see that we can have semiconductors that lie between the conductors and insulators, right? So if you have studied the electronics, you may have studied the p-n junction, right? So we actually use the doping method to create the semiconductors, p-n junctions, okay? So that has the properties that lie between the conductors and the insulators, right? So when you give them a voltage, at certain voltage they resist, and then there's a breakdown, and then they start conducting, right? So diode and transistors, they are under these categories, right? Just like silicon and germanium, we use these semiconductors to do the doping, and then we have the holes, and then we have the carriers, right? So we try to create the deficiencies and the abundance of the charged particles, right? So the charged places. So when you have there is a p-n junction or depletion region between them, and when you apply the voltage, it resists until the breakdown occurs at the junction, and then you have a flow, right? But the good thing about semiconductors is, or the advantage that we get is, they are some sort of unidirectional devices, just like diodes, right? So when you apply a negative voltage, they resist the flow of electrons, right? So it's like a one-way gate, okay? So that's the basic we study in the digital electronics. So I'm not going into the details, but we are discussing the conductivity. So the conductivity in semiconductors is due to the doping. We have electrons and we have holes, right? So holes mean deficiencies, right? If you remove one particle, one electron from a place, then there's a hole. That means there's a deficiency, and that material still require one more to fill up the space. And then we have electrons. That means the negative charge carriers. These are the number. And then we can have the in the conductor, because we are not dealing with holes and electrons only. We can only have one at a time. So we can say that those are equal to n, mu, and e, right? So E is the charge, and mu e is the mobility. So that mobility again depends upon the structure of that material itself, right? How many free electrons, right? And then how it polarizes to the external electric field. And n is the number. Now again we have J is equal to sigma E for a perfect conductor, right? So the perfect conductor, we assume that the J over E is equal to sigma, right? And we assume that for a perfect conductor, sigma approaches to infinity, correct? And of course, the J cannot approach infinity. So E has to approach zero, right? That means that even with a very, very small or negligible amount of electric field, still you can achieve a high amount of electric the sigma, right? So the infinite amount of sigma means that infinite amount of the J, right? So that's the ideal characteristic of a perfect conductor, right? So that means that it will not have any opposition to the flow of charges. This is an example, okay? So you can see. Let me show you some of the. So So in the first video, we saw that we applied the high voltage to the electrical in high power insulators. So these insulators, we actually designed those materials that provide the mechanical coupling between the power line and the ground terminal, right? And the power line can rest on those terminal, or even they can be suspended. And the idea is actually to get rid of the impact of the high electric field, right? So a conventional insulators does not work here because it's a high voltage line. So there is a high voltage and high amplitude of the electric field. Amplitude of electric field is high. That means that it can jump from one point to another easily. Now, you might think that how this happens, right? Because there is an insulating air, right? So of course there's air between them, right? There's the gap between the terminal and the ground. Maybe it's a few centimeters, right? So how can it jump? So you remember that there is a always some material between the two terminals, right? So that is usually the air, right? And in the previous test, you saw that it works for normal phenomena, but as the time passes, so there are pollutants in the air that changes the epsilon naught of the air, right? And also the material that exhibits the ER, right? So total epsilon is epsilon naught times the epsilon R, right? That actually helps the E to jump from one point to another. That kind of a polarization we will study later, okay? But look at the design actually that will help you to understand the E pattern. So how the dipoles from the one terminal can jump to another, right? Sometimes we also use the same name of electric field with the electric field voltage. That's what we call VBR, right? We call the breakdown voltage, right? So what's the maximum voltage required to break this material? So as we discussed before, materials, they do not conduct the electricity, right? So they oppose the electric field. But the problem is there is a certain limit. So when if you keep on increasing the E, right? So the materials inside, they usually make dipoles, right? So they all the atoms inside the material, they have positive and negative electrons and protons, right? And actually they are balanced in number. But when you put a huge electric field, what they do is they arrange themselves in the opposition of the electric field, and they try to hold it because the forces inside the material are extremely strong as compared to the conductors. That's the difference between insulator and there is still a limit. They have to hold it until the external field does not put them apart, right? So there is a limit, few megavolts per meter. There's a limit. And then when the limit exceeds, you can see that the electric field can destroy even the porcelain, even the mica, even the glass, even the wood, and even the air. That's the reason you will see the flat. You see that if there is a few meters of a distance between the earth point and the high voltage point, but they can still jump and they can find the arcs, right? That's the polarization in the air. So the air molecules, they actually get polarized and then there's a breakdown. So air 3 into 10 raised power 3. That's the limit for the air molecules to resist against the breakdown. So you see now this video will show you the pattern of the electric field that actually is crucial for designing a specific shape, right? So why can't we make it solid and why can't we make just a long line, right? So there's a reason behind why need to make them curve. This is exactly the reason that we discussed in the dipole contact, right? So the positive and negative, they have field patterns. So field is perpendicular to the surface. So you have to see So you might have also seen that the capacitor is not only a device; it's an effect, right? So it can be experienced in transmission lines, power transmission line, and even in your ordinary transmission line. Even a circuit kit can act like a transfer the capacitor. For example, you have a semiconductor circuit, right? A simple board, and you see that it has a common ground, and there are certain connecting materials, and between the positive and negative there is again a dielectric material that is used to place all the electronic chips. So again it acts like as a capacitor, right? So capacitance is a kind of a phenomena, right? So this analysis helps us to understand this. Okay, so we will keep on exploring this. This is a simple electric circuit problem, so we can use the formulas that we have derived here to find out the current, the J current density and charge density. Now, let's again utilize our own uh, idea of the voltage and electric field on a simple electric circuit. So you have a piece of a conductor. Let's say you connect it with some voltage. The length is L. The current density is J. Remember, this is not amperes. Amperes per meter square. And E is your electric field. And if you want to find out voltage, again use E dot dl formula. X1, X2 as a length. Just use the Cartesian system and use an E times L is the voltage. And current density is J dot ds, and then area is A. The J is comes from the current density, and you plug all the value, you get sigma EA. So J is sigma E comes from the Ohm's law. Now we have the voltage, we have the current, and the resistance is V over I. So you have E dot dl, E dot ds. Now let's see the resistance. So if you have the electric field and the length, you have the area, you can find out the resistance. Now, if you want to see in the form of a Joule's law, you can again multiply E and J and dV, you get the power. Okay. And simply we have in simple cases, like say in the electric circuit, we can use I square R. Now, we can also build the same idea in the instrumentation. If you look at the different type of instrumentations, you would see that uh, we can create the resistance equivalent of any physical quantity. For example, pressure or force. Uh, Here is a piezoelectric sensor function diagram where a force can create change in resistance. Now, if you put more force, the material stretches, and if you leave it, then the material has some fixed value, right? If you compress, the resistance decreases, right? So you can see that the resistance is directly proportional to F. The overall phenomena is R is equal to R naught. R naught is here. 1 plus alpha F over A naught. This is the constant or the coefficient, right? So this comes from the sensor. You can see that if there's no force, it stays at flat. When you stretch it, the effective area or the length increases. And that's how you can create from the metal wire, we call it serpentine wire. Okay. So when you have a force, it increases the length. So when the length is increased, the resistance increases. So next question is how to transform so force gives change in resistance. Now change resistance into voltage, right? So you connect a voltage source into a Wheatstone bridge and connect your output here, right? So what happens is without any disturbances in the arm, if all these four resistors are same, there's no voltage here. Okay, so when you plug some sensor here and you apply a force, resistance changes, and then the resistance initially, which was R naught, it changes with delta R. Any change in resistance will change the balance point of the bridge, and you can have your meter here that has some needle, and then will show you the force in terms of voltage. Okay. And for a modern instrumentation, you can use this, and you can use from an IC where you can change from analog to digital, and then you can use some display computer microcontroller. You can easily display the value in terms of a digital. Okay. Now, so because we have seen the videos, so let's dig up more inside the construction of the dielectric material. Okay. So we want to see some interesting insights. So as you can see here, that's the state of the atom when there's nothing, right? So that's the neutral state. So there's no electric field. So you have a positive nucleus because of the protons. You have free electrons surrounding the nucleus, and that's the complete electron. So in under the normal circumstances, there's a balance. The number of plus and the number of negative are same. So the internal electric field is zero. There's no electric field. Now, what happens if you provide an external electric field, right? So the electric field actually disturbs the balance between the previous construction of the atom. So the charged particles, they feel more uh, force from the E, right? So now the center of the cloud that was actually in some position where it is balancing now has moved. Now, this actually creates some electric dipole, that the positive charge accumulation and the negative charge accumulation, now they are displaced with some distance. Now, this happens at atomic level. Now, again, look at the structure of the material. Okay. Now, when you apply electric field E, okay, so these are the structures or the patterns inside the material. See that at every stage there's a dipole, right? So all the atoms now they are producing small amount of their own electric field, right? Not shown here, but you see that they are aligned according to the electric field externally provided. Okay, so you see that positive, 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 positive. So positives are more aligned at this position, and all the negatives are aligned at this position, such that minus plus minus plus minus plus and minus plus. Okay, now what happens is that now there are two electric fields. Okay, one is the external, one is the internal electric field that is produced due to the polarization. This one. So this is the electric field due to dipole. We learned previously, right? So we assume that there are two charges displaced apart, so they will produce some electric field. Correct? Now you would see that this electric field due to the dipole interacts with the E field provided externally. Correct? That's the reason we use the epsilon to the measure of the electric displacement field D. Right? That's the reason people invented D. Otherwise, E was also necessary, right? So we have electric field, right? D is equal to epsilon not E, right? We have learned this. So, so that's the formula, right? Right. So these two quantities, they act quite similar, but at certain point they are very different. People need their understood their requirements, why we need to develop it. So this is electric field, and this is epsilon naught free air. Remember, this is free space. That means that when you have an electric field, right, and the material inside just here, right, then E and D are directly proportional to each other, correct? But if it's not air, if it's the material, then what happens? that the material itself polarizes and it produces its own internal electric field. That's field what we call is the polarization field. Okay, due to the dipoles. So due to the dipole, we have now the polarization field. So there's derivation in physics, but we are not going. Now we need some new quantity we call density, right? So in physics, we usually prefer to call it the displacement field. Now this is equal to the free air, not E, field polarization. Understand? Is it clear? Now, this P is what we call the, sometimes we call the electrostatic induced field. This is done by E. So this P is now equal to epsilon xe times E. This is called the susceptibility. Now, this is another constant. Okay, now this defines how good is your material in terms of facilitating the polarization. Sometimes if you provide a lot of field and material, is that enough? It's not polarizing, right? And again, there's another new technology, what we call the material science, that's helped us understand the structures or internal composition, chemical composition of the material itself, right? So how the electrons are placed inside and how they can produce the electric field, polarization field when the electric field is provided. So there could be the structures like isotropic structures, linear structures. Now, we are not going into that detail, but that constant actually help us to determine the effect of polarization due to the electric field. Okay. Now, put this value here, and then you'll get epsilon xe and this one. Take epsilon constant and you add 1 plus xe. Now, what is this? That's the E, simple E, rather than epsilon, right? Now, this E is when you use some material, any material, it other than the air. So this is your epsilon when you use air. Okay. Now, E is relative, right? So you have epsilon is equal to epsilon naught times epsilon r. Some materials for air, we use ER equals to 1. That's standard. So now everything is related with respect to air. Okay, let me. So you can find some list. Okay, so this is the permeability. So we are looking for permeability. Okay, here you see. So we have list of all the different parameters. See, so glass is 3.7 into 10 is power minus 10, right? Ice. So all the materials they have permeability, permittivity. Remember, the same phenomena we can apply to the other materials. For example, if we are trying to characterize materials in terms of facilitating the electric field and the polarization field, and we combine these two into the new formula we call epsilon, then it will tell us the electric field concept. But if we are going to see the magnetization property or characteristic of the materials, so how good the material get magnetized when it's opposed to the magnetic field, then we use permeability, mu r. Okay. And the third thing, when we are trying to understand the flow of charges inside the material when exposed to electric field, we look at the conductivity. So conductivity helps us to understand the conductors when we are trying to make cables. Okay. The permittivity help us to design insulators. It helps us to understand and analyze the capacitors, right? So when we are trying to design the insulator, we need some breakdown voltage. So we use this guy to help us. Okay. If we are trying to design some capacitors, or we are trying to do some energy storage to have some capacitive effect, then we try to find out this one. And later I show you this helps us to compute the capacitors. Capacitors help us to compute energy, and energy help us to run the machine wireless, okay, cordless. Okay. And the third thing is the permeability that we will study in our next chapter. That is the property of the material in terms of magnetic properties, right? Well, the iron is good, or maybe iron is good, maybe the copper is good, maybe the aluminum is good. How they behave in terms of, so these are the three main characteristic properties of materials. Okay. You should have a clear the differentiation, and maybe important. Okay. So, so that's the distinction for materials in terms of uh, the the permittivity. Now, this is the breakdown, right? Uh, I would like to show you the breakdown if I have the video. Breakdown in wood. So you see that breakdown can occur anywhere. Okay, it can occur in the uh, for example, please listen carefully. So in exam, if I set up a problem, right, that is something related to the electric field and the distance, okay, you should quickly understand that this is something related to the breakdown. Okay. So in every exam, I change the statements. I started from the spark plug. So spark plug have positive and negative terminal, and there's a space between them. That the breakdown occurs. Okay. So because the voltage has to jump. Okay. So the formula is same. V is equal to E times D. Every time you have to use the same formula. So either your voltage is given, electric field is given, find the distance, or distance is given, voltage is given, find the electric field. So I will not use the term electric field. I will ask, find out the breakdown voltage under this distance and this voltage. Okay. So, and sometimes I can use the example of a simple semiconductors. I can give you that you have developed certain charge, and then how much voltage you require to prevent it from breakdown. And also, of course, there's some rainy season, or there's some clouds, they develop certain voltage, right? And then if the distance from the ground is this, what's the breakdown, something like that. Okay. So in every phenomena, V equals to ED can be applied. Okay. Now just look at the breakdown. So how it polarizes and breaks the internal structure of the insulator. Okay. So that's high voltage. That's the ground. negative. So as you can see that now, this is the material, okay? So this is the positive and negative, and there's electric field, okay? So electric field is trying to break down the internal properties of the material, okay? So the material can no longer resist against the high electric field. So what happens after the breakdown voltage, right? So it is something more than polarization field, okay? So the material, so so the material actually tried to resist against the polarization field, okay? But because the E was so high, so it damages the internal bonds or the electrons, and it pulls all the electrons because the force was so high. That's the reason it produces the heat, and then you see that now that wood is no longer a wood, right? So it changes the structure. Now you can see that uh, Earth, at sea level, the air can sustain up to 3 megavolts per meter. Now you can understand. So if you have a 3 megavolts within 1 meter, and if the dielectric between the two terminal is air, so it can jump after this value. So that means that when you are designing something, maybe you should keep 50% safety limit. Okay, so maybe you put 2 meters within 3 megavolt per meter. Okay, so if your value is 3 megavolt per meter, the electric field is 3 megavolt per meter, right? You should at least keep 2 meter distance. So that's the 50% limit. Now, you see relative permittivity we discussed in the previous slide, right? That's epsilon naught multiplied by ER, which is equal to E. Okay. Now this actually includes the P field polarization, right? Now, if you multiply this with electric field, you will get the displacement field. That's the reason we use D and E both. Okay. So E will give you the standard value, and D will give you something related to the material. Now you see that the mica can stand 5 point, that's the relative permittivity, and the strength is 200 megavolts. Glass is 25 to 40, bakelite, quartz, and then the other materials. See, that's the reason we use uh, most of the insulator based on the mica. Now, there's another an interesting phenomenon. Okay, uh, I would like you to show you another video, and I will not explain it. So I would suggest you see the video and try to understand. Okay. Okay, that's one setup. Okay, one type of experiment, that is electromagnetic waves. Okay, that's another case in electrostatistic case. Okay, it's valid on both phenomena. Okay, but please pay attention to this one. Now, you saw that, right? There are plenty of applications, right? So let's say if there is a thunderstorm and you feel there's a danger of getting the lightning, it's better to stay inside the car. Okay, that's another application. Okay, so we saw two different phenomena. One is electrostatic, another is electromagnetic. Electromagnetic means that if there are electromagnetic waves, that's just like a radio waves, right? Then you can block this radio wave inside the cage. But it's also true for the electrostatic. That means if you have a extremely high voltage electrostatic terminal, right, that can actually produce spark to a certain body, certain equipment, right? So you place someone into a metallic body and you can be, protect it. It's just like a cage. You protect the prisoner from the outside effect. In the previous videos, we saw that the electric field is so strong and it can, burn something, it can damage something. But now, how a cage can prevent? I need some answer. You can Let's do. I give this question in the exam. That's the reason. So we have a conductor. We have a conductor. So first thing you should know that when we have a charge accumulation on the surface, right? So you connect some terminals, and we know that the charges or the charge density, it goes on the surface, right? There's no charge inside. Okay, one thing. So the charges are on the surface such that the electric field is perpendicular to the surface. We have developed that concept earlier. Okay, now uh, if you have this charge densities, right, then you possibly have this type of uh, the electric field, correct? And for the negative, charge density, the field vectors are going here, and for positive, they are going here, right? So let's say it's going like this. Okay. Now we learned that the polarization or the dipole also has the field. right? The P field polarization, right? We learned that when you apply an external electric field, so this is like external electric field. Remember, this is the cage, and this is your external field. So the field like this, right? It goes like this. So when it enters, it's negative. When it leaves, it's positive. All right. Now, so this dipole has its own electric field. So this and this will cancel, right? So you only have field going in and then going out, or in technically field going in and then moving up and then moving down and then leaving the prisoner unharmed. We call it Faraday's cage. It's applicable to both electrostatic plus electromagnetic. Okay. Now, in the video, you might have seen something very beautiful. I want to show you the. You see the shielding. You see, that's the shielding, right? So the question is, what is what is the electric field inside the conductor? So the electric field inside the conductor is zero. So that's your conductor cage. Okay. So the electric field from, let's say you have a Wi-Fi signal, okay, and you have also this, say, cable going through the room, right? So we have Wi-Fi signals here. So they are bumping on it, right? So that's it, electromagnetic. We will study this time varying fields later, okay? Let's say you have time varying fields. So they will produce something here. If it is not present, they will strike on this, and then if you are running some transmission on your TV, if this is your video signal, you cannot see. It will produce noise, just like you have seen the old audio transmission or video transmission or the cable transmission that requires cable. But if you have this cage over the cable, right? So this will neutralize the effect of external electric field. So this field and this field, they cancel, and then it goes outside and the internal conductor is saved. Okay. The same thing happens to the aeroplane, right? So you see that the aeroplanes, they go through the clouds, right? So the clouds usually have, you seen that even in the bad weather, they have a huge charge accumulation, and they are looking for something to discharge, right? So the airplane can go there, right? Even though it's not terminal grounded, right? So it's a very rare chance to get the neutralization of the charges through the plane, but still it has some volume, right? But it can affect the electronics inside, but it totally gets saved, and that's the reason, because the outer shielding protects it from the external E field, and then the inside the conductor is totally safe, right? So you would see that there are plenty of applications, right? So mostly all the electronic devices or the electrical equipments, you just create a cage, and then inside it is just zero. So it protects the equipment, it protects the the all the things. Okay, so the electric field inside the conductor is zero, and Faraday cage is a beautiful example. Now, that's the same thing that I was talking to you, that if you have a metal sphere, right, and if you have some external field, right, so it will produce some polarization, and some part will get positive, some get negative, and then they are getting separated, but inside there's no field. Remember, the negative charges will distribute themselves in such a position that the E field is always 90-degree perpendicular. Okay. Okay. You see, that's the reason. You see those patterns. Okay, so you can visualize those example also. Now, as we have learned, what's capacitor? So when you have two plates or two terminals, right, and they are separated by some distance d. Okay, now you can place air, you can place any other uh, dielectric between them. You can place some material, maybe some paper, mica, glass, whatever. And when you provide some voltage, it will develop charge on its plates, and all those plates or these two conductors, they will deposit charge on their surfaces, and not only deposited charge, but that charge, they will have some electric field between them. Okay, and they will continue to keep this electric field even though you remove the voltage source. Okay, that's the capacitance, that's the capacitor. Okay, so there are plenty of applications, but we would see that how in electrostatic this will help us. So we know that the capacitance, we derived that the capacitance is charge over voltage. So how much charge it develops and how much voltage you have. So for example, if it develops 1 coulomb of charge when you provide 1 volt, it's called 1 farad. Okay, 1 farad. So usually the capacitance is in microfarads. Okay, it's very, very small. So again, we use our electrostatic equations. E dot dl is for the voltage, E dot ds times sigma is the electric field. And then you can have the capacitance here in terms of the electric field. And you can multiply RC to get the time constant. Uh, this is something which is very important in terms of transient responses. Remember, capacitors, they develop the charge and they keep the voltage across their terminals. And the way they store the energy is half CV square. So the higher the capacitance, the higher energy they store, right? But the problem is when you connect to the load, they will quickly discharge. Okay, so when you have a load, let's say some LED or some bulb, they will quickly discharge. And the time rate they will discharge and they will follow the exponential decay is depending upon the RC. That's the sigma over the permittivity over sigma. Now remember this equation, and I'll give you another important idea. So you see that the way the time constant of the capacitor is designed is just because of the sigma, the and the epsilon. Okay, now this is the capacitance and breakdown voltage of a parallel plate capacitor. So you have this capacitor with area A, another plate with same area. They are separated with distance d. The charge density is positive, charge density is negative. Connect to some voltage, right? So you see that the field is straight. Remember, rho s over epsilon naught is the electric field between two plates, right? And on the corners, we have some deformable field. We call it fringing, because the corners, they change the place, right? So that's why the E has to go perpendicular. Now, apply the formula V is equal to EDL, you get ED. Now, this is important, okay? This is, always remember this equation. I think in midterm, we also use this thing, okay? So capacitance is charge over voltage, Q over ED. So capacitance is now equals to epsilon A over D. So epsilon is something related to between plates. So what is in between plates? Mica, air, gas, whatever. And A is the area of the place and the D is the distance. That means that now you can increase the capacitance if you can make capacitor bigger, right? Or you can increase the epsilon, right? Extremely high quality material. C increases with decreasing the distance, keep them more closer, okay? Now, the dielectric strength of the material according to the table is 30 more megavolt per meter for quartz. So the breakdown voltage is EDS, right? So if the distance is this and E is this, then you need this voltage 3 into 10 raised power 5. What does it mean? It means that you connect some voltage here, 5 volt, 10, 20, 25, 30, 35, 40, 45, keep on increasing, 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 right? Because there's some material here. It is trying to resist against the E field. And when it reaches 3 into 10 raised power 5 volt, it will break down and it will, the collapse between, there's a collapse between two plates. Okay. The polarization will no longer exist. Okay. That's how you find the polarization, or sorry, the breakdown. We can use the similar Gauss's law, right? Now you see this is a cylindrical shape. Therefore, we have RDR here. Okay, we can use E here, E from the main Gauss's law and V from the chapter to find out that the capacitance of a coaxial line is this. So that means you need inner and outer distances between the coaxial cable to find out the capacitance. Okay, this is just an application, just for your reference. Okay, now we have more contents regarding the capacitor, right? So I want to show you that the capacitors uh, and the batteries, they both serve somehow similar purpose, okay, but not the same. For example, batteries are used to store the energy, right? So batteries store energy. They again hold the charge. And when you connect to the load, they supply the power, okay? DC power, let's say. Now, capacitors does exactly the same purpose. You provide them the voltage and you can easily charge them within the 1 second, right? When the capacitor is fully charged, you can use it to the load and then it can quickly discharge. Both can charge, both can discharge, both can provide energy. But there's some fundamental difference. One difference is that the capacitor holds the electric field between the plates in terms of a dielectric and the electric field. But the battery does this operation in terms of electrolytic process, some chemical process, right? So it takes the power of the ions, right, to provide the charge that is being previously stored in terms of the charging. So when you charge, you push the charge, the positive ions towards the one end, negative towards the another end. And then you connect the load, the same amount of energy is released in terms of that electrolytic process. But the energy density is given by epsilon v square of 2 density d square, which is permittivity, applied voltage, density of insulating material. Now look at why we are interested in energy density. That means that how much energy it can provide with per kilogram. So mica has the highest dielectric strength, 2 into 10 to the power 8 volt per meter. Let's use this one. If we select a voltage rating of 1 volt and a breakdown voltage, let's say 2 volt for the safety, this will require that D be no smaller than 10 nanometer for mica. Let's say sigma is 6 times epsilon naught, 6 times bigger than the relative permittivity, right? So the density is 3 into 10 raised by 3 kilogram per meter cube. Let's compute the energy density. So energy density is 2.5 into 10 raised by minus 2 watt hour per kilogram, right? That means that with the lithium ion battery, it's 4 times less than. So lithium ion battery is 4 times better than in terms of providing the energy. And that's true. And that's true. The reason is that the battery is designed to provide small power for a long duration of time. So you can use battery maybe for 12 hours without charging. Capacitor, you can't use maybe more than few seconds. Okay. So another thing, when battery is discharged, it still keeps the voltage. When the capacitor is discharged, it drops the voltage, charges and then discharges. So the capacitor is designed to charge and discharge frequently. That's the reason we use it in the electronic circuits to filter the high frequency components. Okay, let's say you have a generator and the generator output is fluctuating. You connect a parallel capacitor, and when the capacitor will charge with the peak and discharge. So it will charge and then it will discharge slowly. So the output is stable. That's how the capacitor filters the fluctuations. So how it filters? It filters based on the charging and discharging. So there's no life cycle of the capacitor. So it can charge and discharge 1,000 times in few minutes. Battery can't do that. So battery, because the battery material has to go through chemical processes, so it degenerates with the time. So you have to replace the material inside that's being used for the electrolysis, right? Therefore, the drawback of the storage of the battery is that you need to replace it. So it does not have duty cycles, enough duty cycle. But the good thing is it can charge, retain the charge for a longer duration. Okay. Now, why I'm telling you this story? Because we need supercapacitors. That is something in between batteries and capacitors. Okay. So that we can create a device that can provide a properties of a capacitor and mixed with the properties of a battery. Okay. So we have plenty of applications, but look at this one. This is the power density. Okay. So the power density is on the x-axis. Energy density is on the y-axis. Okay. So the batteries are good in terms of the uh, energy densities, very high. But in power density, they are on the lower scale, right? Uh, Capacitors, very good in power because high voltage, power is equal to VI, but the duration is very short, right? So they can pump up a flash. Have you seen the camera flash? Right. So you just use 12-volt battery in your DSLRs, and it can flash very high, right? So they can provide an impulse, huge amount of voltage and current. Now the problem is they can't do it for a longer time, right? So these are at two corners. So we need something super capacitors that can have a properties of a capacitor in terms of a power, and they have some properties of a battery in terms of the energy. So the design comes with the hybrid construction of both the modules. So you can see that the energy of the capacitor is half CV squared. That means if you have more capacitance, you have more energy, right? And C is equal to epsilon naught E over D squared. A over D, right? So now you see the physical construction area. You need a bigger area. You need a less separation. You need a good material, and then you can increase the C, right? So batteries do this with the electrolysis. So you can combine the two physical demonstrations and then put them into form of a supercapacitor. Okay. So let's see some. Also tell you some polarization. Okay. That's the some theoretical knowledge about the capacitor and how the material between the plates can affect the capacitance and result into the energy storage. So there are furthermore sensors based on the capacitance, for example, to measure the fluid gauge, for measure the humidity. So you can see the capacitance in terms of the pressure sensor, so how it changes the capacitance, and then that can result into a change in quantity, right? So I would recommend you go through all those devices, because in exam we do ask some uh, case study based question and then ask you to analyze it. Okay, so let's take a quick break, and then we will discuss the midterm. Okay.